Can you survive this chemistry course without having to do a whole bunch of memorization? I think you can. And one of the main ways is to make sure that you fundamentally understand the underlying principles of the chemistry material. Throughout this course, you're going to do many calculations. You could try to memorize many of the formulas, but I argue that a more reliable way is to understand the underlying principles of the calculation, and in particular, understand the idea of unit conversions. Therefore, in this chem activity, I'm going to show you how to use units as a guide in doing calculations. Our intended learning outcome is that you are able to use conversion factors to convert between different quantities. Let's take a look at the teaching model 1, in which case we are looking at the fuel efficiency for the 2019 Terbium Roadhog, which of course is an imaginary car. We have some details about this car. On the highway, the Terbium Roadhog has a 23.2 kilometer per liter rating in terms of the gasoline consumption. The gas tank has a maximum capacity of 45.5 liters, which represents the size of the gas tank. We will assume a cost of gas in the Okanagan to be about $1.35. Often when you're asked to do a calculation, it is posed as a question, and sometimes students get a little mixed up on where to start. In the example here, I would like to start a little differently. In this case, I'm not going to ask you a particular question to solve, but rather I'm going to ask you to look at the numbers that are here and think about, well, what could we calculate? How could we combine these numbers? One of the places I'd like you to consider starting is with the quantity that's given. We have 45.5 liter gas tank. We have some other numbers which are represented as ratios. That is, both of the numbers have some value per liter. So let's try multiplying the 45.5 liters by the $1.35 per liter and see what we get. When I multiply these two numbers, I get a price of $61.4. Without reflecting too much on what this means just yet, let's see if there's another calculation we can also do, starting with the initial quantity of 45.5 liters. If we multiply the 45.5 liters by 23.2 kilometers per liter, we arrive at 1,055.6 kilometers. I'm only allowed 3 sig figs here, so we have actually 1.06 times 10 to the 3 kilometers. Now we're going to step back and ask, well, what do these numbers actually mean? What questions am I answering? We started with the size of the gas tank, and we multiplied that number by the current cost of gas, and we arrived at a certain price. As you might imagine, we've just calculated how much it would cost us to fill the tank of gas. So if I had asked you the question, how much would it cost to fill a tank of gas, this would be the mathematical calculation that would be required. On the other hand, the other number, of course, is a distance. The question we are answering is, if we were to burn all the fuel in that tank, how far, what distance could we actually travel? I think it is important when you do a calculation to keep in mind two things. One, the units can guide us in developing the correct mathematical approach. And two, the end result should be consistent with the original goal of the calculation. Is it a cost or a distance that I'm trying to calculate? While not always true, it is often helpful to identify a given quantity in a problem and to notice that one or more conversion factors will be required to convert this quantity into a new quantity. In our example, the initial quantity had the units of volume in liters. When I multiply by a conversion factor where in the denominator I also have the units of volume in liters, of course then the units of liters are going to cancel. The resulting unit will be the unit that is in the numerator. That is, a quantity in dollars or a quantity in kilometers. Many of the calculations that you will be doing will have this format. Quantity multiplied by a conversion factor will result in a new quantity. With that little bit of introduction, let's move on to the teaching model 2, where we will explore these ideas a bit further. Here we have definitions of the inch and of the foot. We make a statement that there are exactly 12 inches in 1 foot, and 1 inch equals 2.5 centimeters. I ask you to examine the corresponding picture of the ruler and then consider the key question numbers 1 and 2. Key question 1 is asking about the significance of the word exact or exactly in a conversion relationship. It is perhaps helpful to consider that exact relationships are not approximations. They are not limited by significant figures or uncertainties, but rather they are agreed upon definitions. These definitions, however, are often arbitrary, but they are universally agreed upon by scientists, and therefore they are useful. By definition, 1 inch equals 2.54 centimeters. This is an exact relationship. The result is not confined by one significant figure. The same, of course, applies to the 12 inches in 1 foot. Other examples, as we will see, include the metric-to-metric conversions involving the metric prefixes. For example, 1 kilogram equals 10 to the 3 grams. Connected to these definitions of the inch and the foot comes 2 conversion factors. For the key question number 2, we're presented with 4 different possible relationships. The question asks you to cancel or cross out those relationships that are not valid. At first, this might seem kind of a silly exercise because 2 of the relationships are clearly not valid. That said, many times when I'm correcting papers, I see these mistakes. We know that there's a relationship between centimeters and inches, but we have to be careful about how we show this relationship. It is always 1 inch per 2.5 centimeters, or 2.5 centimeters per 1 inch. Therefore, this relationship and this relationship are not valid. We are left with 2 conversion factors, which allow us to convert between centimeters and inches. Both of them are equally important, and we can use both of these. They're not equivalent in the sense that 2.54 divided by 1 or 1 divided by 2.54 do not give the exact same numbers in terms of mathematical calculation. But the fact that we say 2.54 centimeters equals 1 inch means that these 2 conversion factors both, in a sense, equal 1. There is unity to their relationship. Let us see when we might use each of these conversion factors. Teaching Model 3 introduces the idea of the unit plan to solve conversion-type problems. At first, I will explicitly emphasize using the unit plan to solve such problems. This initially may seem rather tedious or extra work in having to write out these things. I ask you to bear with me, at least for now, as later we will phase out the explicit use of the unit plan. Later, we will use it more implicitly as we write out the appropriate calculations. The unit plan guides us in thinking about how to make the calculations. The unit plan, for instance, to convert from inches to centimeters would be inches, arrow, to centimeters. The arrow represents the conversion factor. In the numerator, we would have centimeters, which are the target units, and then in the denominator, we would have inches. The idea is that we want the unit inches to cancel out, so that we are left with the unit centimeters. We complete the conversion factor by writing 2.5 centimeters per 1 inch. Let us apply this idea to key question 3. I'm well aware that many of you will have done many of these sorts of exercises, but I am also aware that some students still have some trouble in knowing where to start in doing more complex examples. So we will start with a simple example and then move on to more challenging examples. We have a basketball player who has a height of 7.10 feet. We want to calculate her height in centimeters. We have to convert feet to centimeters. I may not know how to do this directly, but I do know how to convert feet to inches, and I know how to convert inches to centimeters. I'll make a unit plan that guides us from feet to inches and inches to centimeters. Across each arrow, of course, will be the conversion factor. In the case of feet to inches, we know that it's 12 inches per 1 foot. I put in the numerator the desired unit. I put in the denominator the unit that's going to be cancelled. Then for inches to centimeter, I put in the numerator the centimeters, and in the denominator the inches. So that would look like 2.54 centimeters per 1 inch. When I ask you to write a unit plan, this is the sort of thing that I'm looking for. Now we can use this to guide us in doing the actual calculation. The actual calculation will involve using the numbers with the appropriate units. The 7.10 feet height of the basketball player is multiplied by the 2 conversion factors, which results in a number with units of centimeters. The feet and inches units cancel. In this particular case, the final number of significant figures, 3, is defined by the initial quantity, that is, the 7.10 feet tall. The conversion factors, as mentioned, are exact relationships, and they do not define the number of significant figures in the final answer. Here is a notation that you may not be familiar with, however. As mentioned, this calculation should result in a number with 3 significant figures. But there will be times when I don't want to round off too soon, as perhaps this result will be used in a subsequent calculation. So I write out all the digits, but I put the extra digits that are not significant as subscripts. As in this case, this is my final answer, I will now round off to 2.16 times 10 to the 2 centimeters. This has been an example of using a unit plan to plan and execute a calculation. It is always good, however, to ask, does your answer make sense? In this case, we're converting from larger units to smaller units. Many more centimeters versus feet are required to represent a certain distance. Therefore, it makes sense that 7.1 feet corresponds to more than 200 centimeters.